Looks like it's a go.
Perfect. Hello, everyone. My name is Sadia Ahmed, and I'll be your host for tonight.
I'm not ready yet. Now go.
Okay.
Hello, everyone. My name is Sadia Ahmed, and I'll be your host for tonight. The topic for this evening is The Other Footprints, Honoring the Apollo Workforce by Burt Dicht. Burt Dicht is a retired aerospace engineer. He is a space historian and a speaker, and also the managing director of membership at National Space Society. Before we start, we will go through some virtual etiquettes. Then we'll go through the NSS announcement, upcoming space forums and town halls. Then we'll jump into our program for today, and then we'll come to the closing. As always, we ask you to submit your questions using Q&A function. You can also use the chat function for your questions. Just be respectful of the panelists and the audience. If you enjoy our program, consider donating for our cause. And you can do that by going to go.nss.org/donate-now. Also, please take a few minutes to complete our NSS survey forum survey, and your feedback is going to help us in planning future events. Now to the NSS announcements. As you know, we had our flagship conference, ISDC 2025, last month, and it was an incredible success, and we had more than 1,000 attendees for the conference. Our featured speakers were astronauts and the space travelers. As you can see in this slide, from the upper left, Sienna Proctor, Jared Isaacman, Suzanne Kilrain, Hood Gibson, Chris Ferguson, and Story Musgrave. We also had 2 new sessions at ISDC for students. One was the Astronaut Scholars Panel and the Rising Star session. Now, as we know, next year is the 100th anniversary of the first flight of liquid fuel rocket by Goddard. And we are celebrating it by hosting a Goddard 100 contest in collaboration with Blue Cube Aerospace. We are accepting entries until January 31st, 2026. We are also welcoming volunteers to help us promote and judge the contest. If you are interested, feel free to contact Francis Delutry at francis.delutry@nss.org. As you see on this slide, you can also scan the QR code and it will directly take you to the website. Our next space forum is on July 31st. That is on Mars Desert Research Station, analog experience with Tim and the crew. And following that, we will have our next space forum on August 7th. That is on Into the Void with John Yuskwaskis and Mel Croft. We'll be looking forward to our space forums after August 7th on Blue Origin Early Career Panel, Astronaut Scholars Panel with Larry Bradley, and Sierra Space for our space forums. Now let's get into our program for today. And I will hand it over to Burt. Our program is on The Other Footprints by Burt Dicht.
Thank you so much, Sadia. Okay, everybody, welcome. Thank you for joining us. It's nice to step out of my moderator role and get into presentations. So I'm going to be sharing my screen right now. Oops, a big mess there. Let's get this. There we go. Let's see. There we go, everybody. Well, thank you so much. Well, I'm going to start off with a spoiler alert in case there's anybody that doesn't remember or know this, that 56 years ago, this Sunday, Apollo 11 landed on the moon, July 20th, 1969. I was 10 years old. I know I look a lot younger than the age that's indicated, but it was a really defining moment for me. I still remember that day very well when they landed in the afternoon and getting ready for the moonwalk in the evening. I remember going outside and looking up at the moon and just wondering, how did they do that? And that put me on the path to become an engineer. But the reality is It is amazing how they done it. There was a huge workforce behind the moon landing, and it really took a nation to do it. There were 400,000 dedicated individuals, engineers, scientists, technicians, many others, even on the business side, accounting, attorneys, uh, technicians. But, again, it took a lot of different people in order to make this possible. 20,000 different companies, universities, and government agencies, everything from rocket design to spacesuit stitching. Every detail mattered. So it was truly a remarkable collaboration of talent, innovation, and determination. And what I want to do tonight is honor all of those individuals who made that possible. It's the other footprints, the footprints that helped get us to the moon to make those footprints on the moon. So we're going to be talking a lot about that tonight. And what I do want to start is take you back to May 25th, 1961. This is when President Kennedy made a speech before Congress on urgent national needs. And we all remember that saying what he said. I believe this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. But not much further in there, in that speech, he made a few other comments. He said, but in a very real sense, it will not be one man going to the moon. If we make this judgment affirmatively, it will be an entire nation. For all of us must work to put him there. And I think that's the key. And when you realize that, he had a really great grasp on what was needed to get us to the moon to meet his goal. And the question is, how do you turn that goal into reality? At the time of his address to Congress, NASA was about 3 years old. It had achieved only 15 minutes of human spaceflight experience, Alan Shepard's suborbital flight. There was no infrastructure, there was no hardware, and all of a sudden, now NASA was tasked with turning this great goal, this aspirational idea, into actual designs and procedures and hardware. And for the workforce, it really sank in fast that it's going to require, wow, whole new systems in order to get us to the moon. And I've got a quote there from a young engineer at the time, Robert Schwinghammer, but he represented the very young NASA workforce at the time. He later became a director at Marshall Space Flight Center, but he said, we were all young, we didn't know what failure meant, and we knew we could do it. And that represented the NASA workforce at the time. And you see that picture of Robert, he's on the far left there. This was a picture from 1965 with Walt Disney and Wernher von Braun at Marshall Space Flight Center. But that, to me, represents what this is all about and why we're honoring all of these great workers. So tonight I'll be talking about a few different things. Let me just give you a disclaimer. I will definitely share the presentation with you. I've put a lot of extra detail into the slides, thinking that you'll have a good record if you'd like to have the slide deck. What I'll be talking about is how do we get to the moon, the Apollo guidance computer, the all-up concept, the lunar module, Apollo spacesuits, the J2 engine. I'm going to focus in on two pioneers that I knew personally, and the 1202 alarm, which a lot of you probably know about already. So let's get right into this. How do you get to the moon? And I'm going to be talking about an individual named John Hobart here. And it's a really interesting story. So getting to the moon, people had speculated for a long time. In the 50s, there were engineers, scientists looking at it. There was a great series in Collier's magazine that had leading scientists and engineers detailing the plan. But now, with Kennedy's goal in mind, this was not just an academic exercise anymore. Now it was national importance. So this decision on how to get to the moon would set the course for everything that would follow. And there were three competing concepts. One was called direct descent. This was launching a massive rocket and spacecraft directly from the Earth, and it would land on the lunar surface, then take off again and return to Earth. That was one approach. There was Earth Orbit Rendezvous. This was a case where we launched multiple smaller rockets. In Earth orbit, they would assemble the spacecraft that would go to the moon, refuel, and head to the moon from there. The final approach was something called lunar orbit rendezvous. This was using two much smaller spacecraft. And I use the terms right now, command service module and lunar module, even though those terms weren't used at the time. It was like mothercraft and lunar lander, but I didn't want to confuse things. But after reaching lunar orbit, two astronauts would transfer to this landing craft and descend to the moon, then return to the mothership in orbit and for the trip home. So each of these had different components to them, and all of them had challenges. And that's what NASA was confronting at the time of this decision. So direct descent, it was a simple mission profile. The main disadvantage of it, it required an enormous launch vehicle and also a large landing vehicle, about the size of an Atlas rocket. And this large launch vehicle, there was a concept, or there were two concepts. They were called the Saturn C8 and the Nova rocket. These rockets would make use of eight F1 engines, which were on the drawing board at the time. F1 engines had 1.5 million pounds of thrust. So do the math. That's 12 million pounds of thrust on this rocket. Huge. It was over 400 feet tall. And people were really worried if there was some explosion on the launch pad, Orlando would become beachfront property. That's how worried they were about the size of this rocket. It was enormous. On Earth Orbit Rendezvous, they could use a smaller rocket that was also in concept called the Saturn V, but they would need two of these rockets. So these rockets would actually meet in orbit. The astronauts would assemble everything and then go on to the moon. But it also required a fairly large lunar lander, about 5 stories tall, in order to do this. But this was one that NASA was leaning toward at the time. The final approach, lunar orbit rendezvous, as I said, very efficient, much smaller. It can make use of just one Saturn V rocket, a lot less mass, but it required lunar orbit rendezvous. So that meant they had to orbit the moon and actually rendezvous and dock in lunar orbit. We didn't know how to do that in Earth orbit, and there was great concern that it would be too challenging and too dangerous. If there was a problem in Earth orbit, they could always somehow get home. Wasn't going to be able to do that if they were in lunar orbit. So NASA immediately rejected direct descent. It would be just too challenging to make this massive Nova rocket. So they passed on that one. But they also passed on lunar orbit rendezvous, determining that it was just too risky. So they rejected that. And then they focused in on Earth orbit rendezvous. That was the preference of NASA leadership at the time. So they're moving forward with the plans to try to work on Earth orbit rendezvous. And there was this man who inserted himself into the discussion. His name was John Hobart. He was the assistant chief of the Dynamic Loads Division at NASA Langley in Virginia. Now, here's the thing. He was not involved as a manager or in the direct planning of Apollo. But he was a dynamicist. And for those friends out there who are engineers, you probably took a dynamics course. He understood motion. He understood the bodies of motion and how they acted upon after forces. And he was studying all the lunar mission architecture. And for him, it was a simple equation. The need to save weight, the need to do this in a certain amount of time, and the need to save money. And he all immediately said lunar orbit rendezvous is the way to go, and he became its chief proponent. Now, again, NASA's opposition to lunar orbit rendezvous centered on its complexity and danger. But there were also other opponents of lunar orbit rendezvous and a couple of heavyweights, including Wernher von Braun and Maxime Berger. Some of you might remember Maxime Berger from my last presentation. He became NASA's chief spacecraft designer. He had designed the Mercury spacecraft. But they were in opposition to trying to do lunar orbit rendezvous. Now, von Braun wasn't the issue of the rendezvous itself. He was a proponent of Earth orbit rendezvous because he saw it as a way to build space infrastructure. If we're going to have to assemble these spacecraft in space, in Earth orbit, we're going to be able to do other things once we land on the moon. So he was looking forward that this is more than just the moon landing. He wanted something, the infrastructure in place to build a space station, to go on to Mars, that type of thing. Now, for Hubble, he believed lunar orbit rendezvous, the risks were manageable, and he really became adamant that the two spacecraft in lunar orbit wasn't just one possible method. He felt it was the only way we were going to meet Kennedy's deadline by the end of the decade. So he began a campaign, and he didn't just propose this. He actually did extensive research and calculations. He was proving his work. He had the numbers, but he was getting no traction. He was at a meeting once with some higher ups, and he pitched lunar orbit rendezvous. And this did not turn out too well. Maxime Berger rose up from his seat, pounded his fist on the table, and he said, "His figures lie, and he doesn't know what he's talking about." So it was a really uncomfortable situation for Hubble, but he wasn't discouraged by that. He decided to do something that for most of us, we probably never would have done. He decided to go outside his chain of command, above several layers of management, and he wrote a letter with all of his calculations, all of his data, to Robert Siemens in Washington, who is the NASA Associate Administrator. And again, would be considered career suicide for most people. What Siemens at first didn't know what to think of this guy. Is he a pest? He started asking questions about him. Who is he? What's he doing? But the letter got his attention, and it kept lunar orbit rendezvous in the discussion. And people all outside started doing the numbers, and they were seeing that Hubble was correct, that the best approach to meet the Kennedy's timeline was lunar orbit rendezvous. One of the last individuals to give in was von Braun, but once that happened, and that was June of '62, so we're talking almost a year after the decision was made to go to the moon, but it became the moon architecture that they were going to choose. Hubble left NASA in 1963 for the private sector, but he was invited back when Apollo 11 was landing on the moon into mission control. And after the landing, von Braun turned to him, shook his hand, and said, "Thank you, John. It is a good idea." So it was really this outsider who set us on the path to get to the moon. So we thank John Hubble for his persistence and his effort to really demonstrate why this was the way to go. Next, I want to talk a little bit about the guidance computer that helped get Apollo to the moon and also helped us land on the moon. So I'm going to talk about Charles Draper, Hal Lanning, and Margaret Hamilton. Now, you would think that the initial contracts that NASA would award might have been for rockets or spacecraft, but no, soon after the Kennedy decision, NASA awarded its first contract to the MIT Instrumentation Laboratory. It's now called the Draper Lab, for the Apollo guidance computer. They thought this would be a long lead item. The lab was headed by Charles Stark Draper. He was a brilliant engineer, professor at MIT. He actually started the lab in order to give his students practical experience. So he was way ahead of his time. So he was working on the concept of an inertial measurement unit to guide aircraft, rockets, missiles internally. And one of his devices was used to navigate a B-29 bomber from Boston to Los Angeles without any use of external navigation tools. Once he proved out the concept, it became commonplace to have an IMU in submarines and ballistic missiles and aircraft. And NASA wanted this type of system for the Apollo spacecraft. What you see there is a picture of the IMU. It's about the size of a basketball. It uses 3 accelerometers to measure linear acceleration around the X, Y, and Z axes. And it uses 3 gyroscopes to measure angular velocity, how fast the device rotates around each axis. When I used to volunteer at the Intrepid, I would show people the IMU in the Growler submarine. It was in the control room. So they were happy to go ahead and start working on this system. And they really didn't think they would have that much trouble with the IMU itself. They thought that that was a manageable engineering task. What worried them was, how do you build a digital computer that the astronauts would use to interface with the IMU so they can receive and input information? They didn't have a spacecraft to go by, so they had to estimate, how big can this thing be? And they came up with the size they thought they could work to, 1 cubic foot. Not very large. I don't know if you all remember the movie Apollo 13, where Tom Hanks as Jim Lovell makes a comment about, and we're getting computers so small they can fit in an entire room. Well, this one would be 1 cubic foot. And it was one of the first computers to use what's called integrated circuits. And one of the great innovations came from the Deputy Associate Director of the lab, Hal Lanning. It was a really interesting approach for the computer to prioritize computing tasks. This would speed up processing. This would later prove really critical when Apollo 11 was doing its powered descent. And we'll talk about that at the very end of the presentation. So the Apollo guidance computer had a memory of only 72 kilobytes. I know people used to joke about your calculator or your watch had more computing power than the Apollo computer, and that is absolutely true. What was interesting about the computer is that it was composed of wires that were woven in certain patterns. This was something called rope memory, and it took expert seamstresses to thread the wires through these magnetic rings. Now, you all know about the bits, binary digits, ones and zeros, and that's how that makes up a computer memory. So a wire going through the ring was a 1, a wire going around the ring was a 0, and that created the memory. These seamstresses did the work. The one drawback, of course, to rope memory is that once it's installed, it can't be changed. So that meant the programming had to be right from the very beginning. And to do that, here comes Margaret Hamilton. She led the team that developed the programming. She had actually been at MIT, worked at MIT in coding and programming on different projects, including weather surveillance, that type of thing. But this was completely new to her. And she said, when I first got into it, nobody knew what it was, nobody knew what it was we were doing. It was like the Wild West. There was no course in it. They didn't teach it. So she led this team of 400 engineers and programmers to come up with the programming for the Apollo guidance computer. On the right, you can see her there inside a mock-up of the command module, but there you see the coding stacked up next to her. 145,000 lines of code were needed. How does that compare to today? Well, the space shuttle's general purpose computers had about 400,000 lines of code. I was trying to find out what the Crew Dragon and what a Falcon 9, best information I could find, their estimates were about 500,000 lines of code for each. But a 787 Dreamliner has 6.5 million lines of code. and an F-35 fighter has about 10 million lines of code. So you can see where they were, but this was the very beginning. There was never a computer quite like this. NASA was a little bit conservative. They decided to use radio navigation to guide Apollo to the moon. But once Apollo went around the moon, and once the lunar module started to descend, it was going to be the Apollo guidance computer that did its work. The big test came on Apollo 8 back in December 1968. And when Apollo 8 reemerged from the far side of the moon after being out of contact with mission control, they did a position check, and it was exactly where it was supposed to be. So it verified the Apollo guidance computer had the spacecraft where it was supposed to be. And it worked very well throughout the entire program of Apollo. Hamilton's work actually led to the development of software engineering as its own discipline. And she later formed some of her own companies. If you'd like to see the code, you can actually go online. I've got a link there that you can go if you're a computer guy or gal. You can go and actually look at the computer code. And again, I'll be sharing the presentation with you. So after we've got that, now let's talk about the all-up concept. And this is about testing the Saturn V and George Miller, who I introduced at my last presentation on on the space shuttle program. So once a decision was made with Lunar Orbit Rendezvous, the linchpin, of course, is a launch vehicle that could propel this mothership, the command service module, and the lunar module to the moon. Tasked with this was Dr. Wernher von Braun, who, brilliant German-born rocket engineer, had led his team at the Marshall Space Flight Center. And the concept for the Saturn V was his. And it was a masterpiece. It was a technological leap over anything that the United States had in its inventory. Up until this point, we were using ballistic missiles to put astronauts into space, the Redstone, the Atlas, and then the Titan for Gemini. The Saturn V had 3 million parts. It was 363 feet tall and weighed 6 million pounds. Used 5 F1 engines, not the 8 of the Nova, which produced 7.5 million pounds of thrust. And one day it would be the most powerful rocket ever launched. Of course, that has now been exceeded by both SLS and the Super Heavy and Starship. But back in 1962, it was just a concept on a drawing board. It did not yet exist. So von Braun and his team, along with the prime contractors, Boeing, North American, Douglas, and Rocketdyne, worked to design, manufacture, and test the Saturn V. It was a massive engineering project, and unfortunately, I left one of the items off about the development of the F1 engine, and maybe I can do that at another time. But it was difficult. You know, they say space is hard. It was a tough job to create the Saturn V. But von Braun was meticulous, and he developed a testing plan for the rocket. He was going to do a step-by-step approach. Launch the first stage alone, possibly using just dummies for the second and third stages. Then after that was successful, launch the first and second stage. Then after that was successful, launch the first, second, and third stage. And then finally, all the rocket with the spacecraft. So that's at least 4 launches right then and there. So that's a lot. And would they be able to do that in the time allotted? Well, George Miller, as I mentioned, who actually led to the Apollo applications and Skylab and also the space shuttle program, at the time he came in from industry. And he had helped develop the Minuteman ballistic missile for the Air Force, and he was brought in as the associate administrator for manned spaceflight at the time. He started doing a top-to-bottom reviews of everything, and one of those things was the Saturn V program. And he really grew concerned over von Braun's testing plan, just forgetting how much it might cost to make all these extra rocket stages. He really questioned, the time it was going to take to do all these tests and launches. And he realized we'll never achieve the end of the decade deadline. So he pitched something to von Braun called the all-up testing concept. It was used on the Minuteman, and the idea of all-up means you launch a fully assembled Saturn V with all of the stages stacked and fueled. And it was an approach, again, that was successful on the Minuteman, but this was going to be much riskier. And von Braun actually actually showed Miller a drawing comparing the two rockets, saying there's no comparison. How can you actually suggest this? But actually, Miller had a really good arguments that von Braun said, well, it sounded reckless to do all up, but his reasoning was really impeccable, because if you're doing these individual tests, you're not getting a true idea of how the rocket would perform once it's fully stacked. So it wouldn't be valid. They wouldn't be valid tests. And Miller said, it was clear to me if we're going to meet President Kennedy's goal of landing on the moon before the end of the decade, we had to take a bold step. And it really was a bold step. So they went through the planning and the timeline, of course. The first launch of the Saturn V all-up testing was in 1967 in November, and it worked pretty well. There was a few things with what they call the pogo effect, and I'll talk about that a little later. But the second test did not go so well, and we're going to be talking about what happened there. But Roger Lanius reported in his history of Apollo, it was an audacious idea, and it worked. But without all-up testing, we would not have made it to the moon in 1969. So kudos to George Miller there. Now let's talk a little bit about this lunar module, this landing craft that actually John Hobart was so important, so instrumental in leading them to that decision. So we'll talk about Tom Kelly and his Grumman design team and the lunar module. So Grumman, of course, was an aircraft company. It's now Northrop Grumman. And when they won the competition, they were excited at first. And then they realized there were really going to be some challenges ahead, because this would be the first spacecraft ever designed to fly solely in space, not through the atmosphere at all. And it had very strict weight limits, but it had to be robust, it had to be reliable, had to carry the two astronauts down to the moon. They had to live there, so it's a shelter, and then return them safely to lunar orbit to dock with the Apollo command module. They initially worked to an estimate of around 30,000 pounds. And if you're an aircraft designer, there's always something called weight creep. And that actually impacted them. The weight started to grow to the point that it wouldn't be feasible anymore to even fly on a Saturn V. So they were looking for a place to cut some weight. And Kelly focused on, you see that image there of a concept of these very large windows. They were large, they were heavy, but they needed to provide the astronauts with a good field of view as they sat in their seats during the landing phase. And some of you might remember the TV show on HBO, From the Earth to the Moon. And they did an episode called Spider, which talked about the development of the lunar module. And this was a key piece of it. I think it's probably one of the best hours of television about engineers that you're ever going to see. And the two images I have here are from Spider. And you see Matt Craven, who plays Tom Kelly, is commenting on the windows and how big they are. So he brought his team together. They tried to talk about it. What can we do to reduce the weight of the lunar module? And they kicked around ideas, and someone came up with a comment. What if we get rid of the seats? Kelly called it a brilliant paradigm shifting question. Were the seats even necessary? There were very limited engine thrusts needed to navigate in the weak gravity of the moon. The astronauts' legs could support them, as they say in the episode of Spider. Legs are a great shock absorber. So removing the seats would have the astronauts stand, and that meant they could be much closer to the windows. So the windows could be a lot smaller, and they'd have a great field of view looking out the window. Also, getting the seats out, all that weight goes out as well, and there's a lot more usable volume inside the lunar module. So several problems were designed with this one stroke. The team spent the night looking at different concepts for the module. They met again, and they made this decision to propose this modification to NASA. There were a few people at NASA who also thought about removing the seats. So it was a joint decision by both NASA and Grumman, and NASA agreed to the change. And the lunar module took on the shape that we know it today. But again, a really interesting question that someone asks. Something so simple made such a big difference. So let's talk a little now about the Apollo spacesuit and Ellie Foraker and the ILC seamstresses. Mentioned the seamstresses earlier about the ones who helped put the rope memory together in the Apollo guidance computer, but seamstresses worked in other areas too. And some of you might know our good friend, Jean Wright, who was a seamstress on the space shuttle program, one of the So sisters. So they've had a long tradition of supporting the space program and getting us to the moon, and also the space shuttle program. It was clear walking on the moon was going to require a different kind of spacesuit. The vacuum of space, the temperature extremes, the dangerous chance of micrometeorites, all of those things posed a great challenge. They needed something more than that silver spacesuit that you see the Mercury astronauts wearing, or the spacesuit that they used for Gemini, when eventually Gemini would be there, kind of a transition. They needed something completely different. And like other technical challenges, the design requirements for such a system didn't yet exist. So NASA also actually asked companies to submit bids for this Apollo spacecraft. 8 companies entered the competition, and there was a real surprise winner. The International Latex Company. They made bras and other women's undergarments, but they were also really good at designing things like this. That they had no experience with spacesuits or working under government contracts, but they were a good choice to come up with a spacesuit. Because they had no experience working in the government, NASA appointed Hamilton Standard to actually oversee their work. Hamilton Standard received the contract for the life support system, the portable life support system. That's the backpack that you see the astronauts wearing. But from the start, it was a really terrible fit. The two teams did not work very well together. The suits they delivered to NASA in 1964 were completely rejected by NASA. They were heavy, bulky, not flexible, and they failed a major test. What would happen if an astronaut fell on their back? Could they get up and stand back up while on the moon? So NASA took a drastic step. They canceled all the contracts with Hamilton Standard. They canceled the contract with ILC and began a new competition. So now ILC was kind of liberated from Hamilton Standard. And they actually proposed a very innovative functional design based on their experience. And they won the suit contract. But this time they reported directly to NASA. Hamilton Standard also retained the portable life support system contract. But this time, they, not being in that kind of relationship, they worked much better together to produce this new spacesuit. So it was actually 3 garments in one. It was a water-cooled undergarment. There was a pressurized inner suit that was flexible, and there was an outer nylon garment that protected against the temperature extremes, and as I said, the micrometeoroids. They tested this suit extensively. It passed all of its requirements, and it was ready for flight. But the key thing here was the work done by these seamstresses. They were an amazing team. They did a lot of overlapping and cross-training and other specialties and expertise. You can see some of their names there. It was really hard work. In most cases, they couldn't use machines. They had to hand sew for safety reasons, some of this. And we're talking about like 17 layers with seams over hundreds of yards using just their fingers. And the tolerances were quite precise within a pinhead. So anything less than perfection was not acceptable. But I also want to talk a little bit about just a person named Errol Ball from Hamilton Standard. This portable life support system also was a technical challenge. So this would provide the oxygen the astronauts needed. It removed carbon dioxide and ensured the astronauts had a comfortable temperature. But a main challenge was maximizing the oxygen capacity with minimal weight. So Earl, like the others before him, said, boy, nobody's done this before. But he produced a brand new system. It was a rebreathing system. It used lithium hydroxide filters. They reacted with the exhaled CO2 that made lithium carbonate and water, and the oxygen then passed through the filter and was recycled. So this reduced the oxygen consumption by more than 20%. So a lot of innovative ideas stemmed from all this new work. But I do want to focus in on one individual from ILC, the seamstress manager, Ellie Foraker. And I love her comment. You know, she's been interviewed. She was interviewed. Never in my wildest dreams would I thought I would be making spacesuits. But she was very demanding, and she made sure the quality was there at the highest standards because the astronauts' lives were on the line. So in that picture there, you can see the suit. It's called the A7L suit. On the left side, it's without that outer layer. Then you see the Buzz Aldrin on the moon with the complete suit, and of course the portable life support system in the backpack. The Apollo suits provided protection for 6 moon landings and enabled more than 160 hours of lunar surface activity. So now let's move on to the J2 engine and Rocketdyne. And I remember I talked a little bit about that all-up testing. So all-up testing was put to the test back in November 1967. The Saturn V made its debut launch on Apollo. It's called Apollo 4. It performed actually pretty well, but there was this pogo stick effect that what was happening, it was sending longitudinal oscillations through the rocket. But everything else worked well. They knew they could figure out a way to solve the pogo stick effect. So because the test went well, they actually took off some of the testing instrumentation for the second flight, which is in April 1968. So just position ourselves where we are in the time frame. Apollo 1 happened in January 1967. So right now, the program itself, from the standpoint of sending astronauts to space, was grounded, but they were moving full ahead with testing the Saturn V. So this second launch, designated Apollo 6, did not go well at all. On the second stage, the S2 stage, which had 5 J2 engines, 2 of the engines shut down. And that meant the other 3 engines had to compensate and actually helped the burn much longer, but helped make sure that the rocket stayed on its trajectory and where it needed to be. So at least they were confident that if there was a problem, the system worked to compensate. But still, there was concern over the J2 engines and why they failed. Then the S4B stage, the third stage, it did its initial burn, getting into orbit, and then it had to do a restart. And the restart was something brand new here. Engines were not made for that, to restart after firing. But this was a key test objective. And the restart was important because that's how you did TLI, or the translunar injection burn, that would propel the spacecraft to the moon and accelerate it to break away from Earth's gravity to 25,000 miles an hour. If that doesn't happen, the mission ends right then and there. So all up is all of a sudden put to the test here. Well, what are they going to do? How do they figure out what went wrong? They figured they could handle the oscillations. The real issue had to do with the J2 engine. The J2 engine was developed by Rocketdyne. It used the liquid hydrogen and liquid oxygen. As I said, it was a key component of the second stage, 5 J2s and one on the third stage, the S4B. I had roughly about 200,000 to 230,000 pounds of thrust in a vacuum. The specific impulse is kind of like your miles per gallon. The higher the specific impulse, the more efficient the rocket engine is. And again, unlike any engine at the time, it was designed to restart, an essential capability needed to put them toward the moon. So the team at Rocketdyne was wondering what happened. The J2 had never failed in any ground tests, and making a diagnosis, of course, is impossible because they don't have any hardware to examine. They did have a clue. There was some telemetry data that pointed to a rupture of a small fuel line that fed what was called the augmented spark igniter. Paul Kastenholz, who was the J2 manager, he would eventually go on to lead Rockwell's team that designed the shuttle's main engine. He led the investigation. And the thing is, they tested the engine over and over again, and it wasn't failing. They were really frustrated. The weight of the entire program is now bearing down on them. They have to get this solved. So his team met, just like Tom Kelly's team met, looking at ideas. And Marshall McClure came up with one of those paradigm shifting questions. He posed a simple question that asked, would it be different in space than on the ground? And that got them to thinking. So they started watching films of their tests, and they saw that ice was building up on the lines carrying the supercooled liquid hydrogen and liquid oxygen. And the fluid lines had bellows that were flexible, so they were susceptible to vibrations. Could the ice itself, which of course needed air to form, be protecting the lines during the ground tests, and that thus preventing the failure? So they used a specialized test chamber to study the components in a vacuum, and sure enough, the fluid lines failed. So it was a simple engineering fix. You can see the old design on the bottom there, right here, and then the new design on the top that took out the bellows. They also put some wire mesh around the lines to strengthen them as well. It was a simple engineering fix, and that solved the problem. And now the Saturn V was ready to carry the astronauts to the moon. So the first test was, of course, Apollo 8, and that was just 8 months later. They were able to take astronauts to the moon, and the Saturn V performed very well in all of its missions after that. So again, a great example of the teamwork of engineers solving these types of problems. So now I want to go into a quick discussion of Hal Walker and Norm Chaffee. And I've had the pleasure of getting to know both of these individuals. Hal Walker, let's see, let me go back there. So Hal Walker was involved in what was called the Lunar Laser Ranging Experiment. And if you're a fan of the Big Bang Theory, you probably saw when the team, when they were sitting on a roof in Pasadena, bouncing a laser off this mirror that was on the moon. That was part of Hal Walker's work. He was a systems engineer at Hughes Aircraft, and he led the team responsible for developing what was called the CORAD laser at Hughes Aircraft. And this was used to conduct that laser ranging test on the moon shortly after the Apollo 11 mission was over. It involved placing this special mirror on the moon's surface to enable a very precise measurement. And of course, judging how fast the laser gets there and then bounces back, they can determine, because we know how fast the speed of light is, how far the moon was from the Earth. And you can see it here on the surface. Buzz Aldrin actually set up the experiment. It was a retroreflector array. It was a bunch of corner cube prisms. And Walker and his team were at the Lick Observatory in California, and they conducted 3 tests firing the laser, and they were able to measure the distances between the Earth and the Moon within a few meters. But with refinements, and this experiment, and they were also carried on Apollo 14 and Apollo 17, we can now measure accurately within millimeters how far the Earth was from the Moon. A really interesting experiment that Hal was behind. He later became a manager again at Hughes, had a great career, retired in 1989, and focused in on STEM education. He formed the African American Male Achievers Network, the STEM International Science Center that he co-founded with his wife to actually get kids interested in STEM careers. And he was invited by President Nelson Mandela to actually establish this kind of program across schools in South Africa. And he moved to Cape Town and was doing a lot of this work. That's where I got to know him because of my involvement with IEEE. And I actually, just like I do with our space forums, I actually did an interview session with him to talk about his experiences. But what I didn't know at the time is that he was also an NSS member, and he formed the Cape Town Society, Space Society chapter. It was just great to get to know him. I never met him in person. We did all of our connection on Zoom and other virtual tools. But I was actually hoping to get him once for a space forum. But Hal passed away in November 2024. Just a great loss. But a true gentleman, amazing guy. And also, I'd like to just also comment on Norm Chaffee. Norm was a chemical engineer by training. He started out in the oil industry in Oklahoma. He didn't know anything about the space program, but he found a position at the Manned Spacecraft Center, of course, now called the Johnson Spacecraft Center in Houston, and decided to do it. He wanted to work in the space program. He worked in what was called the Propulsion and Power Division, and he worked on the reaction control systems for Mercury, Gemini, Apollo, and the Space Shuttle. The RCS, those were small rockets that enabled the astronauts to precisely maneuver and position the spacecraft. So you can see what they look like. These were on the side of the command service module. Norm is there holding one of the rockets, and he spent 34 years at NASA before retiring in 1996. And I had a chance to meet him. He was a very good friend of our former COO who passed away last year, Anita Gale. And we actually had a board meeting there in in Texas at the Johnson Space Center. And Norm gave us a tour of the Saturn V rocket and talked about what he did. And he carried that sample rocket there. I actually enlisted his help when I was working at IEEE to actually speak to students. I was running a summer institute at students at Texas A&M, students at Rice, and we toured the Space Center. And Norm was unbelievable with these students. He devoted his life to STEM education, to mentoring. He just was amazing with them. And there are the arrows pointing to him with a bunch of students. I'm there in the blue. So again, again, both Norm and Hal not only contributed to Apollo, but what they're doing, what they did after they retired to inspire the next generation. So I'm proud to have known them both. So really exciting. So now, as we move into our final piece here, what's called the 1202 alarm. So Steve Bales and Jack Garman, I'm going to highlight what they did. Now, we all know Mission Control. Mission Control located in Houston at the Johnson Space Center, then the Manned Spacecraft Center. It's the operational nurse center for the Apollo and the shuttle and ISS. And it's responsible for monitoring and managing the entire mission, launch to splashdown. So everything from the system's trajectory to crew health. And typically they worked in 3 shifts to make sure there was 24/7 coverage. There were specialized controllers at each console. They were responsible for critical spacecraft systems like guidance, environmental control, propulsion, communications, and they had to work really rapidly in order to solve problems. And you know what they did in Apollo 13 and how they brought the crew back home. So, all the communication that goes between the Earth and the spacecraft goes through mission control, and there's a capsule communicator who is the only person who speaks directly to the astronaut. And the Capcom is an astronaut themselves, so they know to speak the right language. So, so what's happening on Apollo 11 right now? So Apollo 11 is at about 50,000 feet above the lunar surface, and they got the go ahead to start what they call their powered descent to the lunar surface. At about 33,000 feet, an alarm sounded, and if you hear the recordings of it, you hear the alarm, and you hear actually Neil Armstrong first says we've got a 12:02 alarm. Buzz Aldrin confirmed 12:02, and this was about 6.5 minutes before before the landing. So an alarm is not a good thing. The computers on the lunar module were not capable of printing any kind of error message in plain English. They used a series of digits, these 4-digit codes. So you see a 12:02. There were hundreds of codes, and in some cases, people had to even look them up to find out what they meant. What was clear is the astronauts didn't know what a 12:02 was, so they radioed to Houston for help. And remember, even at 186,000 miles per second, the speed of light, to get that radio signal, it took about 2.5 seconds for the message to reach mission control. Then, they had to figure out, what is this? What is this 12:02? There was maybe about 15 to 20 seconds to make a determination. Otherwise, the astronauts might need to abort the landing. So the person on the ground who was monitoring that control station at Mission Control was a 26-year-old flight controller named Steve Bales, and all eyes turned to him. All of a sudden, this is all up to him. Now, what people don't know, or maybe they didn't know at the time, was that behind Mission Control were these back rooms, and with a lot of different experts in these areas that would assist the controllers. So Steve Bell's backroom counterpart was a 24-year-old named Jack Garman, and they both needed to respond to what this 12:02 alarm was, because the rest of Mission Control was clueless, including the flight director. Now, Garman had a list of every error code, and Bales and he had actually contacted MIT to get this list, and they kept it handy. Plus, Bales had once seen a 12:02 in a simulation, so he knew what it was. What was happening is the LEMS computer was being intermittently overloaded, and uh, and and that in itself was not a problem, because remember what I talked about Hal Lanning and his team. They designed it with what they called preemptive multitasking. So as long as it was only intermittent, the landing could continue. So with just about 9 or 10 seconds after receiving Armstrong's message, Bales asked the Capcom, who is Charlie Duke, to inform the astronauts, we are go on that alarm. And that allowed the astronauts to continue. They actually had a few more alarms along the way down. What they later found out, and it wasn't an error on the astronauts' part, they on purpose they kept the ascent module's radar on, just in case they had to do an abort and go up and rendezvous with the command service module. And they thought that was a safety measure to help the astronauts, so they'd had one less thing to do. But it overloaded the computer. But because of that multitasking ability and because of Steve Bales and Jack Garman, the Eagle had landed. So at 4:17:40 p.m. Eastern Daylight Time, the Eagle landed at Tranquility Base, and Neil Armstrong made his one small step later that night at 10:56 p.m. Eastern Daylight Time. A really exciting time. So as I look back on, and these are just a sampling of some of the amazing stories that got us to the moon. And again, it's as President Kennedy said, for all of us must work to put him there. And it took vision, it took courage, brilliance, and as I say, countless hands and hearts. These engineers, these technicians, these seamstresses, coders, controllers, every contribution mattered. The astronauts who risked everything, we thank them, but it was these quiet heroes behind the scenes that made this all possible. So because of them, we didn't just reach the moon, we took our first steps beyond Earth to the stars. So I just want to say on this 56th anniversary, we're forever in their debt and want to thank them for what they did to get us there. And when I go back and I look up at, remember, I looked up at the moon and wonder how they did it. Wow, it's amazing how they did it. They made it look easy, but it really wasn't. It was an amazing task. So, again, as I send this out, I've got a long list of reading for you on histories of Apollo, Apollo astronauts and key personnel, also the women of Apollo, other books that highlight minorities' contribution in civil rights, and the broader social context for Apollo. I have all these books, so I highly recommend them. And also some for more information here, some links for you. So if this is a fun presentation to do, hopefully that you enjoyed it. And now we do have a little time. I know it took a little longer than I thought, so I'm glad I dropped a few of the sessions I was planning to present, and we can get into some questions now. So I'll stop sharing, and we can go into some questions.
Thank you, Bert. That was very informative. So my first question for you is, what was the hiring process like? Were people told they were building rockets, and was it seen as unimaginable during that time?
Yes, the hiring practice was definitely they were told that this was a rocket that or rocket program they were working on. A lot of people didn't have direct knowledge of it, but and it did sound, kind of impossible. But like Robert Schwinghammer, they said we can do this. So I don't think it discouraged anybody when they found out that it was, that this is what they're going to be doing. In fact, it inspired them.
Yeah, okay.
Yes.
Okay, so another question from the audience is, what happened to the Apollo workforce after Apollo 17?
Oh boy, that's sad because as the Apollo program wound down, there were other things happening in the country as well. The Vietnam War was winding down, which was a good thing. But what happened is that the mass layoffs happened, and a lot of people who, after doing an amazing job, some of them were laid off. Some of them stayed on, but it was not a good thing to happen after the Nixon administration when it came in. Actually, they canceled Apollo 18, 19, and 20 to save money, and they decided that that was enough, and so a lot of people did lose their jobs, unfortunately, and some recovered, some got back in, some actually went on to do other types of engineering.
Interesting. Okay, so we have some question about comparison of Artemis with the Apollo. So it says, will the Artemis program be able to live up to the legacy of its big brother Apollo?
Oh, wow, that's a that one's a tough one. I don't know. I don't know. Apollo had an advantage, a national goal set by the president, global, global political implications So we needed to actually beat the Soviets to the moon. So
Mhm.
there was a strong impetus to get us to the moon and be first. That doesn't seem to exist with Artemis. I know that the new administration is, at least in their skinny budget, we're going to cut off Artemis at its third flight, and then figure out another way to get us to the moon after that. But if you're really going to do that, you need to start right now. Uh,
Mhm.
and and unfortunately, I don't know, at this point, I really can't say it will live up to Apollo. I hope it does. I want us to go back to the moon, and I hope we make that decision to follow through. A lot of work has been done, a lot of good work, but I do understand there are cost implications, and we're just going to have to see how that plays out at this point.
But isn't the Artemis it has a bigger scope than Apollo? So shouldn't it be a bigger program itself?
Not really. It does have a bigger scope in terms of the whole idea now is to, instead of just putting footprints and flags on the moon, the idea is to stay.
Mhm.
So that has certain implications as well. But the funding just isn't there at the level we had for Apollo. And a lot of that has to do with how much this is costing at this point. The whole Apollo program cost about 40 billion. And when you factor in today's dollars, uh, but right now, the commitment and the funding just isn't there to make this happen. And there's a lot of work involved. I know we did it once before, but it really will take a good effort to get us back. And I can say right now too, China is really committed to going to the moon. They've got a really sustainable space program that they're working toward, and they're hoping to get to the moon around 2030. So I don't know whether that's going to, are we going to get there or will they get there first? We'll have to, but even now, it doesn't have that same national imperative that it did to beat the Soviets, because that was Cold War.
Interesting.
Yep.
Okay, so another question is, where did the rumor about the Saturn V blueprints being lost come from?
That is an interesting question. I had never heard that before when I saw that answered. So I did a little research. And the rumor, they believe, started because people wanted to resurrect the Saturn V. They said, well, we had a great rocket. We should just resurrect the Saturn V. And people said, well, it's not that easy. Even if you have the blueprints, the machinery, the tooling, the know-how that goes into it that people have didn't exist anymore. So it really was no way to resurrect the Saturn V. And I think that somehow got translated in that the blueprints were gone. There were I think I read somewhere, I don't know how many pages of documents related to Saturn V development. We're talking about 3 million parts. There's a lot. And so they weren't lost. They're there still. But I think someone interpreted an answer and made it seem like, oh, they were all lost. But it just isn't feasible to try to resurrect the Saturn V. Plus, it's 1970s technology, and we've gone way past that. So you wouldn't want to do that anyway.
Sure. So in your talk, you talked about Margaret Hamilton.
Yes.
So we also have another name attached to Apollo, that is Frances Poppy Northcutt. Did she worked with Margaret Hamilton, and what was her contribution into the
What
program?
was the name?
Frances Poppy Northcutt. Poppy
Oh
Northcutt?
no, no, she was actually a flight controller in Houston at the Johnson Space Center, and so she did not work directly. Margaret Hamilton worked at the Draper at the Draper Labs or the MIT labs. Poppy was a NASA employee, and she later actually when she left NASA, she went on to become an attorney. And I actually had a chance to meet her at an event. I think it was around for the 40th, might have been for the 40th anniversary of Apollo. But yeah, she did not work together with with Margaret Hamilton.
Interesting. So another question is, what disciplines were most important during Apollo, which are most critical now?
I don't think we could single out any discipline that was more important. I think it took a team. So I mentioned John Hobart, who was a dynamicist. He was actually a civil engineer by training. Uh,
Mm-hmm.
so you had mechanical engineers, you had electrical engineers, you had computer engineers, technicians, actually scientists and physicists. Uh, there were so many different people involved. I would not single out any one group. I think it was a team effort, and that was really involved in doing this. So. And I think it's the same today. Today, engineering is multidisciplinary. You need a lot of different people working a lot of different teams in order to get things done. So, the great things that SpaceX is doing with its rockets returning and landing, really smart, good engineering with a lot of different people doing a lot of different things. So I wouldn't want to single out any discipline here.
Interesting. So what is the ultimate plan for lunar exploration? What will the moon mean to us in 2050 and 2100?
That's a good question. It really depends on what we decide to do. I think most of the plans are, and certainly from the standpoint of National Space Society, we would like to see the moon settled. We would like to see long-term settlements on the moon and having people living and working there. Again, the idea of Artemis is go back to the South Pole of the moon because we think there's water there, water ice. And if that's the case, then we can get oxygen and hydrogen to eventually maybe propel ourselves to Mars and use the moon as a staging off point. So hard to say where we might be. I think when people look back on Apollo and think about it's been over 50 years since we've been there, that all that time, what we could have accomplished until then. So I'm hoping that the next 20 to 30 years will be a lot different and we'll make this commitment. But it will take a national effort. It's I think that's really a key to this.
Mhm.
So we'll see.
Yeah.
I don't know if I'll see it. I don't know if I'll be around to see it. I hope so.
Then the next one is, how much geological material was retrieved during Apollo, and is it still used in scientific research?
Yes, they brought back 842 pounds of moon rock, uh,
Mm.
and uh, and one of the things that is interesting about NASA is NASA turned a lot of these rocks over to scientists from all over the world to examine it. There's still moon rock that hasn't been examined, and they've got a whole new program to engage the newest scientists. So yes, they are still passing the moon rocks out, and scientists today are still evaluating it. Understand, it's important if we're going to go back to the moon to have a better understanding. One of the big issues is the regolith that sticks to everything.
Mhm.
So they're doing some experiments to see if they can control that. So understanding the moon is really going to be important as we go back. So yes, all these years later, they are still looking at these moon rocks.
Interesting. I have a question from Carl Hirko. He's saying, was there a problem with LEM takeoff?
Which with the what takeoff?
LEM.
The LEM takeoff
Yeah.
from does he say what is there more to that question? I'm not sure I understand it.
The next question he asked, that was there the problem with LEM fuel supply?
No, there were never any issues with the lunar module taking off from the moon and returning the astronauts to dock with the command module. The only time there was a concern on the fuel was during the Apollo 11 landing. Uh, there was an error that was put in inadvertently, and the lunar module actually came down slightly off from where it was supposed to be. And so Neil Armstrong is confronted with a boulder range all of a sudden, and he couldn't land there. So he started flying over the lunar surface horizontally across the lunar surface to try to find a place to land. And they were running out of fuel. Now they could abort any time, but once it got down to a certain amount, they could any time in the landing phase they could abort and go back. So mission control, Charlie Duke is reading out the fuel, 60 seconds, 30 seconds, to let Neil Armstrong know he needed to put it down on the ground. That was the only time I'm aware of they actually worried about the fuel situation. Other than that, I don't and maybe someone else knows. I don't recall any other cases where that happened.
Interesting. We have a question from Brent, and he says, why was there so much time between the landing and actual emerging from the lunar module?
Actually, it was much shortened. The astronauts were supposed to go through a sleep phase and get some rest, but Armstrong and Aldrin were just too hyped up. So they actually moved up the lunar landing. So they landed around 4:17, and 7 hours later they were out. But they had to do a lot of work. They had to do a lot of prep to get ready for the landing, and I mean for the moonwalk and so on. But even then, it was actually much faster than NASA had anticipated.
Oh,
Yes,
interesting.
yes. So there, it might seem like there was a long delay, but it was actually shorter than was actually planned.
Interesting. We have a question about your presentation. Someone said that who created the presentation background graphics?
I found that it's amazing what you can do if you're persistent, and I'm glad to share that. But yeah, it's pretty cool. I thought the backgrounds were pretty nice. It has a lot of great imagery in it, and I wanted to do something that was different than the last time. So actually found that one on one of these sites where they have different templates for PowerPoint.
Someone wants to know, I think Logan, are you aware of Cynthia Wells?
Cynthia Wells?
Mm-hmm.
No, I'm not. Any more information about Cynthia?
I think she was a co-op student from University of Houston. She calculated the amount of fuel for the lunar landing of Apollo 11.
Oh, wow. Okay. So she was an intern there at the Space Center at the time. I'll have to look her up. That sounds great. There are a lot of great stories about things like that. So thanks for sharing that.
Yeah. So I think I would end with the last question about, are there more in-person events planned near Washington, D.C.?
Okay, that's an NSS question.
Right.
Uh, we are going to be doing the International Space Development Conference next June in Washington. So that's our big event. So you can look forward to that. But we also hold the March Storm in Washington, where we go visit members of Congress and senators. So definitely, and that's in March. So we'll be providing that information. So anyone who's living in Washington, you're certainly welcome to do that and join us. I see there were any other questions that maybe where we've got a few more minutes. Should we try one or two more?
Sure. Let's see. Let's pick up from the audience in our Q&A. Let's do this one. When did the idea of dropping the command module to save the lunar module's descent fuel first come about?
I'm not sure I understand that question.
So the idea of dropping the command module to save the lunar module's descent fuel.
No connection to that, you know. There's no connection to the lunar module's fuel capability was internal to itself. It had nothing to do with anything related to the command service module. So everything is playing out precisely when they would undock. They would do systems checks. They would descend a certain amount. And as I said, start their powered descent at 50,000 feet. Once mission control said everything is in good shape there. So yeah, there's no connection there. I see someone has raised their hand. Should we let's see if we can let Donald ask a question.
Sure.
Let's see there. I can allow to talk here. So Donald, I think we allowed you to talk, so you'll have to go off of mute.
Okay. Are you
There
hearing
you go.
now?
Yeah, I hear you.
Yeah.
Yeah.
What I'll tell you what telling that on Apollo 11 and 12, they used the descent engine to drop the command module from the 69-mile circle to the 69 by 9 mile by 10 descent orbit, right?
I do not know that.
Yeah, but that originally intending to start on Apollo 13, but because of the abort, they didn't. So starting on Apollo 14, they dropped the dock command and lunar modules into the descent orbit, stayed in that orbit for the next day. Then the command module separated and circularized, and then they went into the power descent. So that extended the hovering time from 30 seconds to a minute. That's what I'm getting at.
Okay, I'm not aware of that, so thank you for sharing that. Yep. Okay, I think there was Logan wants to ask a question as well. So let's do that. Okay, and we'll make him allowed to talk. So maybe this will be the last question.
Sure.
Okay, allow you to talk. Okay, Logan, I think you're on.
Yeah, I just wanted to elaborate on Cynthia Wells. So she's one of these real hidden figures. She's a local Houston resident.
Okay.
But she actually, as a co-op student with NASA, as it was mentioned, she later became the NASA engineer assigned to the LIM environmental control systems as the task manager. So she was actually managing like 12 men who were like 20 years older than herself. But the thing that I think is amazing is she was a member of a team called the Consumable Analyst Group. And she actually studied the use of the LIM as a lifeboat years before Apollo 13. And though that study was ridiculed by her peers, Section Chief Don Nelson actually delivered that study to Mission Control after the explosion. To what extent that study was used during the mission, I do not know, but I've always had that question, and I haven't been able to find out. In fact, I've asked Fred Hayes about it. He wasn't in the know about how that study played a role in his mission. But I just put that out to you because she actually is still alive. She still is a resident of Houston, so she's on Facebook. If
I'll definitely check her out.
Connect with her.
Yeah, thanks for sharing that. Absolutely.
You're welcome.
Okay. Well, very good. With that, Sadia, thank you so much for moderating.
And thank you.
I'm going to turn it back over to you. Yeah, you're welcome.
Yeah, it was an amazing presentation. And I would like to thank everyone who has joined our NSS forum. And whichever time zone you are, have a great evening, day, and the weekend.